All right, y'all, let's non-dimensionalize an equation. Our problem here is presented in this nice big wall of text, except it's not just a wall of text, it's full of juicy, relevant information, so I'm going to read the whole thing. Room ventilation is an important application of fluid mechanics. Imagine a room of volume V. Let's assume the room is a cube, so it has a length L on each side. A source of air pollution S releases pollution at a steady rate in units of mass per time. So what could this be? This could be cigarette smoke. This could be carbon monoxide from a leaky oven or an unvented lantern, kerosene lamp, something like that. It could be fumes from cleaning products, all kinds of not nice things. Fresh air enters the room at a flow rate V dot, and polluted air exhaust leaves the room at the same rate. By the way, by V dot, I mean V with a dot over it is how we would normally write this. The program I am using to do this video can't really format equations. So polluted air exhaust leaves the room at the same rate, which, by the way, is what we would expect. We're not expecting the density of air in the room to change. We're assuming air is more or less incompressible, so therefore the same amount of air has to leave as comes in. Let me see, we let C represent the mass concentration of contaminant in the air and assume air in the room is well mixed enough that C is the same throughout the room, even as it changes with time. So what does that mean? That means C is the same here and here, but they both change as time goes on. Pollutants are also absorbed by the surfaces in the room, walls, floor, furniture, etc., with a total surface area, A sub S, and is described by, this absorption is described by an absorption coefficient, K sub W, with units of length per time. The most important thing we want to know is when the pollution concentration will reach C limit, the maximum mass concentration that is not harmful. And the differential equation for mass concentration in the room as a function of time is V dc times dc dt is equal to S minus V dot times C minus C times A sub S times K sub W. I'm going to rewrite this in a way that might be a little bit easier for y'all to follow. And that would be, just a second. Okay, so V times dc dt is equal to S minus V dot C minus C A sub S K sub W. Just as a quick check to make sure that this equation makes sense, we have dc dt times V. That's going to give us mass per time. Okay, so this is the mass of the pollutant in the room changing per time is what that is. And so S is also mass per time from the problem statement. V dot times C, that'll be mass per time. And then C times A sub S, so that'll be mass per length cubed times length squared, that's mass per length, times length per time, which was the kW units, and we get mass per time. Incidentally, now you can see why the units of kW may seem a little random. It's because it makes this work out. And so we have the pollutant going into the room minus the pollutants leaving the air in the room, either through the exhaust or through the surfaces. Put all those together and you get the accumulation of pollutant over time. So all of that checks out and makes sense. If I were to draw a picture of this, it would look sort of like this. You would have air going in at V dot and out at V dot. You would have the source S sort of going into the air in the room, and then you would have CASKW coming out. Okay, lovely. So non-dimensionalizing an equation, this is a kind of problem that really does work best when you more or less follow an algorithm with set steps. And those steps are, we list all the relevant variables and constants and then we figure out what dimensions they use. Select scaling parameters. One per primary dimension. Define non-dimensionalized variables, plug in, rearrange. All right, and so we're going to do this for this problem. Now, so we start by listing all the relevant variables and constants. In real life, if you were doing this, you would know the equation you were trying to non-dimensionalize, and you would need to think about what sort of constants are relevant. But for problems we're going to do, you know what constants are relevant because I give them to you in the problem. So it's a little bit fictional because the only information you have in the world is what I give you, where in real life you have to find the information you need and figure out what's important. But in this case, as I said, but my problem also mentions L and C limit. The problem gives you that information. So let's list variables and variables and constants. So what variables are in this problem? C, concentration, and T, time. And then what constants are important? The volume of the room, the S, the rate of pollutant entering the room, V dot, AS, KW, all of those are in the equation itself. It's nice to have a length variable that's simple as opposed to volume that's cubed. We'll see that in a second. All right, so let's look at what the dimensions are here. We have C, so that's mass per length cubed. We have time, that's time. We have V, that's length cubed. We have S, that's mass per time. We have V dot, that's length cubed for time. We have AS, that's length squared. We have KW, that's length per time. We have length, that is, well, that's length, yes. And we have C limit, which is mass per length cubed. So clearly the primary dimensions we are dealing with here are mass, length, time. All right. So now we need to select our scaling parameters. And we have 3 primary dimensions. So let's pick 3 scaling parameters that cover all of those dimensions. The easiest one is the room length L. Right, we need something to cover length. We would prefer something simpler to something more complex, so we prefer L to V cubed. Now we need to cover M and T. Okay, so how are we going to cover M and T? And there are, technically, we could choose any 2 variables or any 2 constants that cover this. So we could choose S and KW, for example. I am going to choose C limit and V dot. Again, any set of 3 that cover everything will work. We try to go for simpler ones if possible. These 3 are a good choice. Okay, so now we need to define non-dimensionalized variables. So buckle in. We start with C star. For C, okay, C star. C star is an easy one. C over C limit. This is a reason to choose C limit as one of our parameters, by the way. It's because we care a lot about the concentration. This makes a nice, simple, non-dimensionalized variable. Okay, T. How are we going to get T? So the scaling parameter we have with T in it is V dot, right? So T times V dot, obviously we'll get rid of our time, but now we've added in a length cubed, so we have to divide by length cubed to deal with that. So where do we move next? Let's look. We have to non-dimensionalize everything that we're not using as a parameter. So V dot, we're using it as a parameter. AS star. What's that going to be? That's going to be regular AS over L squared. Pretty simple. KW star. That is going to be, so that's length over time. So let's take KW, divide it by V dot to get rid of that over time. And now we have L cubed, or L over L cubed, so times L squared. All right, check that. Think about it. You will know that that is dimensionless. Have I missed any? I have missed S. So S star will equal S over C limit to get rid of the mass over V dot to get rid of the time, and then the lengths cubed and C limit and V dot cancel each other, so we're good. So let's check. We have C, T, V, S, AS, and KW. Okay, beautiful. So let's go back to our equation now. It was okay. So let's just go through first and rearrange all of these. Or yeah, let's go back to our equation. It was V dC dt is equal to s minus v dot c minus c as kw. Okay, so how are we going to non-dimensionalize this equation? We are going to take each of the values in this equation. We are going to solve for them in terms of these dimensionless variables we defined, and we are going to plug in, all right? So v is in this equation. What will we replace it with? Oh, hey, we didn't do v. We will replace it with v star L cubed. C is in this equation. We will replace it with C star C limit. T is in this equation. We will replace it with T star L cubed over V dot. Again, I am just solving, solving for these variables and constants using these relationships I set up. Let's see, V dot is in this equation, but that's one for scaling parameters. AS is in this equation. We will replace it with AS star L squared. And finally, KW is in this equation. We will replace it with KW star V dot over L squared. Beautiful. So look at that. Think about it, pause and copy them down if that is what you need. Now, again, this is our equation. We will plug in all of those expressions we just developed. So v gets replaced by v star L cubed, C gets replaced by C star C limit, T gets replaced by T star L cubed over V dot, S by S star C limit V dot. Okay. V dot stays in, but C gets replaced by C star C limit minus, okay, so C, so that's C star C limit times AS, so that's AS star L squared times KW, so that's KW star V dot over L squared. And looking at this, I can already see something I can cancel out. And that is L squared here and here. And I also see that I can cancel out L cubed here and here, because we have an L cubed on top and we have an L cubed on bottom. So we can cancel those out. All right, so let's rewrite this, simplifying it all out. We get, and I'm going to pull all of the constants to the front in this case. So we get C limit that I am pulling out of the top right there times V dot. Okay, it gets flipped up to there, times V star dC star dt star is equal to C limit V dot S star minus C limit V dot C star minus C limit V dot C star AS star KW star. And oh look, C limit V stars in every term. What a coincidence. It's not a coincidence. This happens because of the way we set up the rules and went through the algorithm to non-dimensionalize everything. That's why that happens. We cancel all that out, and we get V star, dC star, dt star is equal to S star minus C star minus C star AS star KW star. So here we have it, a non-dimensionalized equation. And so if, for example, you were modeling the ventilation in a room and then you publish your findings in a scientific journal, you might present them like this in a nice non-dimensionalized form.